Assalamualaikum and very good morning class. From this week onward, I will be teaching you this class taking over from PM Dr. Liza. I am Dr. Robia from RFTI. This week and next week, I will teach you topics on Fourier series, and if you refer to our textbook by Navi, it will be in chapter 7. Basically, in Fourier series, we will discuss on topics such as 1. Introduction to periodic functions, harmonics, and Fourier series. Number 2. Fourier series expansion, trigonometric Fourier series, finding Fourier series coefficients, and waveform symmetry. And 3. Examples on trigonometric Fourier series. And lastly, exponential Fourier series and time shift. What is a periodic function? By referring to figure below, the sine function ft is a periodic function where it repeats its value in regular interval capital T, and the equation for this periodic function is ft equal ft plus capital T, where t equals 2 pi. Some examples of periodic functions are in these two slides. The first one is called full rectified sine wave. The signal is commonly found in communication receivers and in power supplies. B. The signal is called sawtooth wave. This type of signal is used to create sounds with subtractive analog and virtual analog music synthesizers. C. The signal is a typical square wave and it acts as a pulse wave that allows duration at its maximum and minimum. And lastly, the signal is called half rectified sine wave, and this type of signal is usually used in a rectifier to construct DC power. Our next topic is on harmonics. The examples of harmonic functions are illustrated below. The first one is the first harmonic with ft equal to 10 sine omega t. This is the fundamental with largest period t equal 2 pi. It completes one cycle in 2 pi, and the amplitude for this harmonic is 10. The second harmonic signal is shown here with ft equal 5 sine 2 omega t. The amplitude is equal to 5 and the period t equal to pi. It has two complete cycles in 2 pi radian. The frequency for this second harmonic is twice the first harmonic. The third harmonics is shown here with ft equal to 3 sine 3 omega t. The amplitude is equal to 3 and the period t equal to 2 pi over 3 with 3 complete cycles in 2 pi radian. The frequency for this harmonic is 3 times the first harmonic. Harmonics are sinusoidal waveforms having frequencies which are multiples of fundamental frequencies. We can deduce that the nth harmonic is defined by ft equal a sine n omega t, where amplitude is equal to a period of 2 pi over n with n complete cycle in 2 pi radian, and the waveform has a frequency that is n times of fundamental frequency. Before we proceed to the next topic, which is introduction on Fourier series, let us look at example 1, which is on periodic functions. In this example 1, we have to define analytically the waveform as shown in the figure. If you look at the figure, the functions, if it starts at 0, it repeats at t equal to 6 seconds. Therefore, the periodic function for this signal is ft equal to ft plus 6. If you look at one period between 0 to 4 seconds, the amplitude is 3, and t between 4 to 6 seconds, the amplitude is 0. Therefore, the equation for this function is shown in this slide. We have two components here. For time between 0 to 4, the ft equal to 3, and for time between 4 to 6 seconds, the ft equal to 0. Now let us move to our next topic, which is Introduction to Fourier Series. Baron Jean-Baptiste Joseph Fourier introduced the idea that any periodic function can be represented by a series of sines and cosines which are harmonically related. As we recall previously, a function ft is said to have period capital T if ft plus capital T equal to ft for all t and the period capital T is equal to 2 pi. In this case, it is enough to consider behavior of the function on the interval between 0 to 2 pi or minus pi to pi. Now let us look at the basic definition of Fourier series. The first one, function fx with period 2 pi must be absolutely integrable over minus pi to pi, and it follows the so-called Dirichlet integral as shown in the equation here. The second one is that suppose the function fx is a single value, piecewise continuous, and piecewise monotonic, having a finite number of maxima and minima. If these two conditions are satisfied, the Fourier series for the function fx exists and converges to the given function. To know more details on basic Fourier series definitions, you can log on to the website as given here. Sinusoids and linear time invariant systems. If we look at the figure, the response of an LTI system to a sinusoid is a sinusoid of the same frequency omega but having a change in amplitude A and phase phi illustrated in the figure. The system is completely described by the way it changes the amplitude and phase of the sinusoid. A periodic signal xt may be represented by an infinite sum of sinusoids or complex exponentials that are harmonics of the original system. The sum may have a finite number of elements or be infinite. Such representation is called Fourier series expansions. To illustrate this, you can look at the example of signals on the next slide. We have here about 4 different types of signals with its harmonics. As we can see here, the first signal is actually composed of many sinusoids that are harmonics of the original system. That's all for this slide. We will continue on the next slide for more introduction on Fourier series. Thank you.